to Concept 3 notes, and we are going to be talking about gas laws. So if you're like, wow, we haven't done math in a while, maybe we're done with math. We are not done. This is where all of the math comes into this unit. And don't be intimidated, you guys. This is so much of the stuff we've already been doing all year. We're just applying it specifically to gases. You're going to have a reference sheet with equations. And remember, the key is just that radar problem-solving strategy I've taught you, where you read the problem, you analyze, and you label, like, what do I know? What do I not know? You diagnose and determine which equation you need. You assess and actually, solve the problem. And then you reflect back and be like, okay, does my answer make sense? We're just going to do that over and over again in some different contexts in this concept, okay? So a little overview. We really can't understand gas laws, which, by the way, I meant to say gas laws are simply just like summarizing the mathematical relationships that exist between things like temperature, pressure, volume, amount of gas, like, ways we can measure gases. We're just summarizing how they all relate to each other. And so hopefully you'll have already done this inquiry activity in class that'll help you be familiar with some of these. But one of the key things, I feel like most students understand the concept of temperature. They understand the concept of volume. But pressure is one that you don't really do a lot of stuff with it in physical science or, middle school science. So pressure is the one that really gets students. So I want to make sure we understand pressure. So pressure is typically represented by a capital P in an equation. And pressure is the force per unit area on a surface. I love this picture. I think it's really helpful. So standing on a mattress, if you remember from physical science, weight is a force. And so you're putting, weight on a small area because it's a force, but it's on a really small area. Whereas here, it's the same weight, it's the same force this man has, but it's spreading out over a larger area, thus it's a lower pressure. Same here. You can look, that's showing how it depends on area. Here's the same with force. So let's say you have a sponge and you put a brick on it. If you barely push it, it's going to be, a weak force impacted on, if you apply a weak force, it's going to be a low pressure on the sponge. But, if you put 2 bricks on the sponge and you increase that force, it's going to make a greater pressure that's going to press into the mattress. So pressure depends on force and it depends on the unit area at which it's applied. Gas particles exert pressure on every surface that they collide with. There's pressure there. If you increase pressure, you're increasing the collisions of particles. And pressure is dependent on volume, temperature, and the number of those particles, because the more particles you have, the more that they are going to collide. Now, there are, I'll fix that little typo right there. There are several ways that we can measure pressure. There's several different units it can be measured in. We can measure it in atmospheres. We can measure it in millimeters of mercury, torrs, pascals, kilopascals, pounds per square inch of area. This is something you'll see PSI if you're doing using a tire pressure gauge on your tire. But this is just simple dimensional analysis. Like if I give you the pressure in torrs, you can convert to pascals. You can convert ATM to PSI. You're just going to do dimensional analysis with conversion factors, which are on your reference sheet. But just to show you, 1 atmosphere, 1 ATM is 760 millimeters of mercury, which is the same as 760 torr. 1.01325 times 10 to the 5th Pascal, which is the same as 101.325 kilopascal. And then 14.700 psi, pounds per square inch. But again, all of these are going to be given to you, so you will be able to convert between these units easily with your reference sheet. Okay, so I said that I mentioned atmospheres. That's the most common unit we're going to be using and seeing for pressure. And you might be thinking what does that mean? Atmospheric pressure is the pressure exerted by the atmosphere, which is kind of like a shell that surrounds the earth, basically on earth. And it's the sum of all the different individual pressures of all the gases that make up the atmosphere, water vapor, carbon dioxide, methane, nitrogen gas, all those different things. Standard atmospheric pressure is considered to be 1 ATM, 1 atmospheric pressure. This is the atmospheric pressure at sea level. Standard temperature, we say, is 273 Kelvin, okay? Or if you're being more precise, 273.15 Kelvin, which we know is 0 degrees Celsius or 32 degrees Fahrenheit. And standard temperature is considered 273 because it's the freezing point of water at sea level and a standard atmospheric pressure of 1 ATM. So if you remember from last unit, I said, 273.15 is more precise. We're just going to use 273. in this class, just I'm trying to help you with sig figs and not overcomplicate it. But your teacher, if you have a different teacher than me, may want you to do the 273.15. So the reason I tell you this is if a practice problem says STP or says at standard temperature and pressure, they mean that this whatever is happening in the practice problem is occurring at 273 Kelvin and 1 ATM. So those are going to be known values that you need to know and reference. Now, real quick, I love this picture because the higher the altitude, the higher you are above sea level, the lower the pressure. People say that air gets thin because it's a lower pressure and the particles are more spread out up there. And there's going to be less of them up there than there are lower. That's what we can see in this picture. Less particles, more particles, and that contributes to the pressure. So that's why I love this picture. But the most important thing from this slide for me is that you understand what STP means. So if you see standard atmosphere or STP, standard temperature and pressure, this is what we're referring to, 273 Kelvin and 1 ATM. Okay, so before we move on, I do want you to practice this, just some pressure conversions. Let's review dimensional analysis, use the reference sheet and the conversion factors given to you, and just practice doing these conversions, and we'll go over them in class. Now, for the rest of the notes, we're going to be covering different gas laws that you need to know. Remember, these are just summarizing patterns we see in gases mathematically based on the variables that, affect them. So this first one is Dalton's law. This is by John Dalton. It's the same Dalton we talked about in Unit 2, the atom, if you remember that. And Dalton's law states that the total pressure of a gas mixture is just the sum of all the partial pressures of the component gases. So all the gases that make it up, we're going to add those together, and that's going to make the total pressure. So if we have two gases, combined, it's just going to add the pressure of both of those, and then that's going to give us the total pressure. So the partial pressure would just be each of these individual gases, like P1, P2, etc. And so if you're going to write an equation, it would just be that the total pressure equals the pressure of one gas plus the partial pressure of a second plus the partial pressure of a third, etc., depending on how many gases there are. So for each of these gas laws, we'll do an example of each of these that you can reference later. And remember, we're just going to be applying radar. All right, so first step of radar, our problem-solving technique that never fails, is we got to read. So oxygen gas with a partial pressure of 301 millimeters of mercury is mixed in a container with chlorine gas that has a partial pressure of 0.649 atmospheres. What is the total pressure inside the container in atmospheres? Well, let's assess the situation, or let's analyze the situation. What do we know and what do we not know? We know that one of the pressures of one of the gases, oxygen, is 301 millimeters of mercury. We know another pressure of another gas, chlorine, is 0.649 atmospheres. What do we want to know? We want to know the total pressure. Okay, so we want to know the total pressure also in ATM, which means we can't add these with mixed units. It'd be like trying to add let's say you were trying to figure out, how much liquid you needed in a recipe, and you're trying to add up liters and ounces. You would need two different measurement tools. It doesn't make sense. You want them in the same unit so you can add them up easily. So we need to make these in the same unit, and we need to make them atmospheres, which means we're going to have to change this millimeters of mercury, convert it to atmospheres. So we need that conversion factor, which if you look up on your reference sheet, 1 atmosphere is equal to 760 millimeters of mercury. Now, is there anything else we know? Yes, we know the equation because of Dalton's law for finding total pressure. And that's where we're going to diagnose. We're going to need this equation. And total pressure is going to be equal to the partial pressure of 1 plus partial pressure of 2. Because there's only 2 gases. That's all we have to do. All right, and then y'all know I like to draw a line just to kind of separate all of our background info for easy reference. This is like the cliff notes of what we read. And now we can actually solve and assess and solve it over here. Okay, so first we got to do that unit conversion. So we're going to convert 301 millimeters of mercury. There are 760 millimeters of mercury in 1 ATM. Remember, we always put like units opposite of each other so that, because this is like a multiplication problem, these will cancel out. We'll be left with only atmospheres. Okay, and now we multiply across the top. 301 times 1 is 301. And then there's just 760 on the bottom over 1, so just 760. And then now we divide. 301 divided by 760 gives me 0.396 ATM. Now, we're not done though. Remember, that is just my first partial pressure just in ATM. Now we're ready to use this equation and solve. So P1 is 0.396 ATM plus P2, which is 0.649. Add those up and we get 1.05 atm as our as our total pressure. All right, that's Dalton's law. Now let's talk about Boyle's law. This law states, this is by Robert Boyle, it states that the volume of a gas is inversely proportional to its pressure if mass and temperature are constant. So like looking at this picture, you can see what that means. So, let's say we have this volume and we have a pressure. If we make the volume smaller this gas, it's going to cause the pressure to go up. As volume goes down, pressure goes up. As volume goes up, pressure goes down. Okay, so it can go either direction. And we can summarize this with an equation. P1 times V1 equals P2 times V2, which the P1 and V1 are just our initial conditions, and P2 and V2 are just our changed conditions. Okay, so let's do an example. All right, first we read, a sample of carbon dioxide gas has a volume of 2.0 liters with a pressure of 3.2 atmospheres. What volume would be needed to decrease the pressure to 1.5 atmospheres? Okay, before you panic, let's just write what we know. Okay, let's analyze the situation. Well, we have an initial volume of this gas, and it's 2.0 liters. And we also have an initial pressure, which is 3.2 atmospheres. We also have a new pressure, a change pressure, so P2, which is 1.5 atmospheres. And what do we want to know? We want to know that volume too. What would be the new volume if we're changing the pressure? Now, we need to diagnose. What equation we use? Well, if we're using P's and V's, if you look at your reference sheet, we're going to use the P1 V1 equals P2 V2. Now, first of all, just think about it. Pressure is going down. Since Boyle's law says that pressure and volume are an inverse relationship, then we should expect if pressure is going down, volume is going to go up. So we should see a bigger number for our volume. Let's see if that happens. Okay, now we're ready to assess. So that's our equation. Now we just plug in. I like best practice to rearrange it first. So I want V2 by itself because that's what I'm looking for. So to get V2 by itself, I need to do the opposite of what's being done to it. Currently, it's being multiplied by P2. So the opposite of multiplication is division. So I'm going to divide both sides by P2. This allows those to cancel out, and I'm left with V2 all by itself, and it equals that P1 V1 over P2. Now I'm ready to plug in. All right, so V2 equals P1, which is 3.2, times V1, which is 2.0, over P2, which is 1.5. And if we solve that, 3.2 times 2.0 is 6.4. Then I got 6.4 over 1.5, and I get 4.3 liters. Is that bigger than the initial volume? Yes. And is that what I expected? Yes. All right, let's learn another one. This is Charles's law by Jacques Charles. And he relates volume and temperature. And he says the volume of a gas is directly proportional to its temperature with a constant mass and pressure. So what that means is if the temperature goes up, the volume goes up. So if we see this here, if we increase the temperature, the balloon, we should expect it to get bigger because the gas inside it is going to need a greater volume if the pressure is going to stay constant. So the equation that represents this is V1 over T1 equals V2 over TU, with V1 and T1 being the initial volume and temperature conditions, V2 and T2 being the changed volume and temperature conditions. Now, something really important here, though, is for this equation to work, temperature must be in Kelvin. Okay, so if you're given the temperature in Celsius, you have to convert it first. And this is the equation on your reference sheet that you're going to use. All right, that's really important. Now, kind of why does this happen? How do I connect this to the kinetic molecular theory? Increasing temperature, we know, increases the kinetic energy of the particles. And then this is going to result in more collisions with the container, which we would expect to increase the pressure, okay? That's, what we would predict would happen. But this says that if pressure is constant, what's going to happen then? Well, if pressure is constant, the volume must increase in order to compensate for that increase in kinetic energy to give them more space without increasing the pressure. So that's how we see that kinetic molecular theory connection. Back to Boyle's law, which I totally meant to say this back here, connecting it to the kinetic molecular theory. If your temperature is not changing, that means the particles are not getting more or less kinetic energy when the volume or pressure is changing. Okay, so the kinetic energy is not changing. But When the volume decreases, the pressure increases because the particles have less room to collide. And so the frequencies of their collisions with each other and the walls will increase, and that's going to increase that pressure. Okay, I always want to bring it back to kinetic molecular theory. And so we see that too with Charles's law. All right, now let's put this into practice with the practice problem. So let's do an example. First, we have to read. Nitrogen gas is cooled from 120 degrees Celsius to 51 degrees Celsius. If its new volume is 65 milliliters, what was its original volume? Okay, well, let's analyze. What do we know? We know the initial temperature was 120 degrees Celsius, and we know the final temperature, the new temperature, is 51 degrees Celsius. Now, if its new volume is 65 milliliters, okay, that means that's our V2. What was its original volume? We're looking for V1. Now, let's diagnose. We have temperatures and we have volumes. If you look at your reference sheet, what's the only equation with temperatures and volumes? It's Charles's, which is V1 over T1 equals V2 over T2. Now, remember the other thing, you cannot put temperature in any of these equations in Celsius. It has to be Kelvin. So we're also going to need to use this equation because we need to convert these temperatures into Kelvin. Okay, so let's do that first. 120 plus 273, that gives me 393 Kelvin. And then 51 plus 273 gives me 324 Kelvin. Okay, so those are my temperatures I'm going to work with. Now we can find volume. So here's our equation. We want just volume 1 by itself. So currently it's being divided by temperature 1. So the opposite of division is multiplication. So we're going to multiply both sides by the original temperature, T1. That allows those to cancel out. And then you get volume 1 by itself. You're left with volume 2 divided by temperature 2 times temperature 1. Now we have what we're looking for isolated on its own, and we're ready to plug in. So volume 2 is 65 milliliters. T2 is, it was 51, but we're not putting that in. It's 324. And then T1 is my 120, which we converted to 393. Now I can solve 65 times 393 divided by 324, and you should get 79 milliliters. Think about it. We said these have a direct relationship. So if temperature is going down, we should expect volume to go down. We're finding the initial volume, so it should be higher if it's going to go down here, which it is. So we know that that went well. That's the part of radar. Remember, the last one is really reflecting and saying, like, is my answer reasonable? Does it make sense? It's kind of a built-in way to double check your answer. Okay, the last individual gas law we're going to look at is Gay-Lussac's law. And this was by Joseph Gay-Lussac, and he looked at the relationship between pressure and temperature and saw that it is directly proportional with a constant mass and volume. And so let's think about why this makes sense, though, with the kinetic molecular theory. If I'm increasing the temperature, I'm increasing the kinetic energy of the particles. And if the volume's not changing, I'm not having any more space for those particles to move. So they're going to collide more, which is going to create higher pressure. Okay, the equation for this is P1 over T1 equals P2 over T2. That's your initial conditions and your changing conditions. And then just like we saw before, temperature must be in Kelvin, Celsius plus 273. All right, let's do a practice problem. Example, if a gas is heated from 231 Kelvin to 317 Kelvin with volume being held constant, what would be the final pressure if the initial pressure was 619 millimeters of mercury? Okay, so what do we know? We know the initial temperature is 231 and the second temperature is 317 Kelvin. Those are already in Kelvin. We won't have to convert them. Woohoo! We want to know final pressure, and we know the initial pressure is 619 millimeters of mercury. But we want to know that P2. So we diagnose, we look up the equations, which one has pressure and temperature. It's this one. We draw our line. We don't need to do any conversions because our temperature is already good to go. So P1 over T1 equals P2 over T2. Now we're looking for P2, so we need to get it by itself, which means we need to get rid of temperature 2. We need to do the opposite of what's being done to it. So it's currently being divided by temperature 2, so we're going to multiply both sides by temperature 2. That allows these variables to cancel out. We're left with P2 by itself equals P1 over T1 times T2. So now we're just plugging in variables. So P1 is 619, T1 is 231, and then T2 is 317. And then we can just solve. 619 times 317 divided by 231 and you should get 849 millimeters of mercury. Now, let's think, does it make sense? Gay-Lussac said that temperature and pressure are directly proportional to each other. So as temperature goes up, pressure should go up. Since temperature is going up in this problem, we should anticipate pressure to go up, and we see that our answer reflects that. All right, now we're going to put it all together, and this is where the combined gas law comes in. This is just going to put pressure and volume and temperature and amount of gas all into one equation, but it's going to expect that the amount of the gas is going to stay constant in order for you to be able to use this equation, okay? So we're not changing the amount of gas, just the other things. And we just put it into one equation. P1 times V1 over T1 equals P2 times V2 over T2. Okay, so let's do a little practice problem with this. First, we read, a sample of an unknown gas has a volume of 2.50 liters, a pressure of 0.861 kilopascals, and a temperature of 299 Kelvin. If the volume is doubled to 5.00 liters and the pressure is reduced to 0.551 kilopascals, what would you expect the temperature to be? Okay, a lot of words, but let's just analyze and see what we know and what we don't know. Just get started labeling. That's the first thing you always do. So what do we know? We know that this gas has a volume of 2.50 liters. We know it has a pressure of 0.861 kilopascals and a temperature of 299 K. Those are all my initial conditions. V1, P1, T1. Now, the new volume gets doubled. So V2 is double. It's 5.00 liters. And then the pressure, P2, gets reduced to 0.551 kilopascals. We're looking for temperature 2. Now, notice our volumes are already in the same units. They're liters and liters, pressures, kilopascals and kilopascals. We don't need to do any conversions there. The only reason you would need to do a conversion there is if like you get one pressure in kilopascals and another in PSI. To use the equation, they got to be in the same unit. Now, the only one you might ever have to convert really then is temperature. It has to be in Kelvin, but they gave us this in Kelvin. So that means our final answer will be in Kelvin. So we're good to go there. So we just diagnosed with our equation. We've got V's, P's, and T's, which means we have to use that combined gas equation like this. So now we just need to rearrange to solve for T2. Okay, so T2 is down here. We need to get it by itself. So first thing we need to do is get it out of these fractions because that'll make it a lot easier. So first, let's just multiply both sides by T2. That will get those to cancel out, and then I'm left with this. Okay, now let's get rid of that other fraction, that T1 that's right there. If I multiply both sides by T1, that will cancel out, and then I'm left with this. Now I want T2 by itself. I should need to get rid of the P1 and V1, so I'm going to divide both sides by P1, V1. Those will cancel out. I'm left with T2 equals P2 times V2 times T1 over P1 times V1. It sounds crazy when you read it like that. But again, we're just following the same problem-solving strategy we've done over and over again this entire school year. Okay, you can do this. So now we just plug in. That's where I like to rearrange first because once the numbers get in, to me, it's more complicated. But if you want to do it differently, that's fine. All right, so there's our equation again. Now let's plug in. P2, now this is like when you write out all the work and do radar, now this part's like so easy. You just refer back and you're plugging and chugging. So P2 is 0.551, V2 is 5.00 liters, T1 is 299, divided by your P1, which is 0.861, times V1, which is 2.50. Multiply across the top and the bottom, and then you just divide. 824 divided by 2.15, and we get a temperature of 383 Kelvin. Okay, now, for the sake of time, we're going to practice in class because that was a lot. I want to practice. I want you guys to digest this. But just for the sake of the video, we're going to keep pushing on because we have a few more things to learn, which I know you're tickled about. Okay, let's talk gas laws and volume. Gay-Lussac, Joseph Gay-Lussac, has another law that we need to mention, and that is his law of combining volumes of gases. And it says that the volumes of gaseous reactants and products can be expressed as small whole number ratios if your temperature and your pressure do not change. And then Amedeo Avogadro, who we know from Avogadro's number, he has a law too that says equal volumes of gases contain equal numbers of molecules. So putting this all together, this means that gas volume is directly proportional to the amount of gas. The more gas you have, the greater the volume is going to be if your temperature and your pressure are constant. And we can put this in an equation where V stands for volume, K is a constant, and then N is the amount of gas in moles. I'm never going to have you do calculations with this though, but here's what I will have you do, and this is why this matters for our purposes. It matters because this whole number ratios, we can use coefficients and chemical equations to tell us the relative number of moles. That's what you've been doing. That's what you did in Unit 6 stoichiometry when you'd be like 3 moles of carbon dioxide to 2 moles of hydrogen gas, or whatever based on the equation. But now we can say we can use it to represent the number of molecules, thanks to Avogadro's law, and we can use it to represent volume. Okay, so for example, look at this equation right here. Hydrogen gas reacting with oxygen gas to make water. The balanced equation is a 2:1:2 ratio. Previously, in Unit 6 stoichiometry, all we would have done here is been like, okay, so you can put this in an equation. You can use like 2 moles of hydrogen gas to 1 mole of oxygen gas, or 2 moles of hydrogen gas for 2 moles of water. Okay, that's what you would have done before. But now what we're saying with these laws is you can also say, if I have 2 liters of hydrogen gas, then that's equal to 2 liters of water. Or for every 2 liters of hydrogen gas, I'm going to need 1 liter of oxygen gas to go with it. So that's a game changer. It's going to help you solve so many more problems because you're going to be able to use these ratios in these equations. Okay? So that's really, really helpful. Now, a definition we need to know is molar volume, and we know this because of those past laws. So molar volume is the volume that 1 mole of a gas occupies at STP, which remember stands for standard temperature and pressure. So standard temperature and pressure, STP, is a temperature of 0 degrees Celsius and a pressure of 1 atm, but we know 0 degrees Celsius is also the same thing as 273 Kelvin. And so this is a constant number. At STP, the volume of 1 mole of any gas is 22.4 liters. And this matters because we can use this in stoic as a conversion factor. So if you have 22.4 liters of oxygen at STP, that means you have 1 mole of oxygen gas at STP. And you remember, we can write these equivalencies as these fractions. 22.4 liters of oxygen over 1 mole of oxygen is the same thing as 1 mole of oxygen over 22.4 liters of oxygen, because these divide by give us an equivalent value of 1. Okay, and so that's really, really helpful. This is very important, which is why it's bolded and has 4 stars next to it, okay? Okay, let's do an example of what this would actually look like then, in terms of like what kind of math you would need to do. So I could ask you, what is the volume of 6.50 moles of hydrogen gas at STP, standard temperature and pressure? So 6.50 moles of hydrogen gas is what we know. We also know that if it's at STP, we know that 1 mole of this would be equal to 22.4 liters. Okay, that's from the last slide. So I want to know the volume of this amount of gas. Well, we're just going to do a conversion. I have 6.5 moles. I know that 1 mole of hydrogen gas is equal to 22.4 liters. That should have a 0 right there, by the way. I'll fix that. Those would cancel out. I just multiply across. Gives me 145.6 liters over 1. Divide by 1, and that gives me 146 liters of hydrogen gas. All right, another way you could see this is, what's the mass of 28.0 liters of helium gas at STP? All right, what do we know? We know we have 28.0 liters of helium. We know that at STP, 1 mole of helium is equal to 22.4 liters of it. Now, I want to know how many grams I have. What's the mass? Well, if I know moles, I can get to mass, which I can get to moles because I have this. How do I go from moles to mass? Well, we bring in molar mass, which is something we, have learned about in previous units. Molar mass for helium, because it's just helium, it's a monoatomic gas, is 4.00 grams per mole. You can look that up on the periodic table. All right, now we have all the information we need. So 28.0 liters of helium. All right, we know that 22.4 liters of helium is the same as 1 mole of helium. Those would cancel. And then with this, we can use molar mass as a ratio. 1 mole of helium is equal to 4.00 grams of helium. That's going to get us to grams, which is what we were originally looking for. So now I just multiply across the top, 28.0 times 1 times 4. And then 22.4 times 1 gives me 22.4. And then I divide, and I get my final answer of 5.00 grams of helium. All right, so here's some practice problems for you to do with this, with molar volume. And then we have one more gas law to learn before we'll stop and practice more, and we'll be done with these notes, okay? And that is the ideal gas law. Now, I know I said that the combined gas law was putting it all together, but the ideal gas law is for real, putting it all together. It's not only just showing the relationship of pressure and volume and temperature, it's also including number of moles of a gas, okay? And this is the equation. It's PV equals nRT. P is your pressure in ATM typically. V is your volume in liters. N is your amount of gas in moles. R is an ideal gas constant, which is 0.0821 with this crazy unit. And then T is your temperature in Kelvin. Now, here's the deal. Pressure and volume and all that, they can be in different units, but then you need a different constant. We are only going to be using the constant of 0.0821 with this unit that you see on your reference sheet. And because this is the unit, that means our volume must be in liters, our pressure must be in ATM, our moles must be in moles, and then Kelvin is for temperature. So you will have to have it in these units to use this equation for our purposes, because I'm only giving you one R value as a constant, but there's other ones too. I just didn't want to confuse you with having to figure out which one to use. Okay? So let's do a practice problem. I think that will help. Let's read. How many moles of gas would be contained in 2.75 liters of gas at 30.0 degrees Celsius and 2.00 ATM? So analyze. What do you know? We know the volume is 2.75 liters. We know the temperature is 30 degrees Celsius, and we know that that's not okay. So we need to know what that is in Kelvin. So you can go ahead and just add 273 and be like, okay, that's 303 Kelvin. We know the pressure is 2.00 ATM, and then we always know this constant because that's a given. We want to know N, which is the moles of gas. So look at your equation sheet. Which equation are we going to use? We're going to use PV equals nRT. So now we just need to rearrange so that N is by itself. So N is currently being multiplied by RT. So we're going to do the opposite of that and divide both sides by RT, and that will get those to cancel out. And it leaves us with N equals PV over RT. Now we just plug and chug, okay? Pressure is 2.00, volume is 2.75 over R, which is 0.0821 times 303 for your temperature. That gives us 5.5 divided by 24.9. And then if you solve that, you get that the number of moles is 0.221. Now, the only other thing that could be asked here is I could say, what's the mass of this? I would have to tell you what the gas is so you could figure out the molar mass, and then you would just do a conversion there. But that would truly be it. All right, but to help you out, we're going to do a practice problem like that. All right, so what's the mass of carbon dioxide? Or what mass of carbon dioxide would fill an 80.0 liter tank at STP, standard temperature and pressure? Okay, so analyze. What do we know? We know the volume is 80.0 liters. We know if it says STP that the standard temperature is 273 Kelvin and standard pressure is 1.00 ATM. We always know R because that's given to us. It's a constant. Now we're looking for grams, the mass of carbon dioxide. To get there, though, we're going to have to know molar mass, and we're going to have to know moles. So the molar mass of carbon dioxide is 1 times the molar mass of carbon, which is 12.01, plus 2, because there's 2 oxygen atoms, of the molar mass of oxygen, which is 16.00. So I get 44.01 grams per mole. From there, if I know the moles, then I use the molar mass to get to grams. Okay, so we're going to work our way backwards here with that PV equals nRT. So let's start by finding the moles. Just like we did before, we're going to isolate moles, and that's PV over RT. We're going to plug it in. Pressure of 1, volume of 80.0 over R, which is 0.0821, times temperature, which is 273. We multiply across the top, multiply across the bottom, and then divide, and you get 3.57 moles of carbon dioxide, but we wanted mass, so we're going to take it one step further, and we're going to do some dimensional analysis. We know the molar mass of carbon dioxide because we already solved for it. So 1 mole of carbon dioxide is equal to 44.01 grams of carbon dioxide. That would get those to cancel out, those moles, multiply across the top and divide by 1, and I get 157 grams of carbon dioxide. All right, there's some practice problems for you, solving for different things using that PV equals nRT. We'll solve for temperature, volume, pressure. We'll go over these in class. And then we will do lots and lots of practice so you will be an expert at using all these gas laws.